Hey everyone. Today we're moving on to the section 2.2, which is limits involving infinity. Okay, limits involving infinity. So, these are sort of special things, but before we actually get to the new stuff, let's just have a quick review to make sure that everyone is on board with limits and evaluating limits. So there's negative 1, 0, 1, 2, 3, 4, 5. Okay, and I'm going to say 1, 2, 3. This goes from here to here, and then I've got this, and then I come across to here, and then I come down to there, and then I hop up to here, and go over to there, and then I come down to here. Okay, so this is f of x, and I'd like to know what's the limit as x approaches 2 for f of x. 5, 4, 3, 2, 1. Well, the limit as x approaches 2, from both sides we're approaching a y value of 2. This is 2. How about the limit as x approaches 3 of f of x? What can we say there? 5, 4, 3, 2, 1. We can say that that does not exist because the limit as x approaches 3 from the positive side does not equal the limit as x approaches 3 from the negative side. Now, I've just made that claim, so maybe you could tell me what is the limit as x approaches 3 from the positive side. Please figure that out. I want to know the limit as x approaches 3 from the positive side of this function. 5, 4, 3, 2, 1. Remember, a limit is a y value. What y value are we approaching as x heads to 3 from the positive? That's 3. And what about this limit as x approaches 3 from the negative side? Well, as I come in from this direction, what's my y value? 5, 4, 3, 2, 1. 1 is the answer. The y value that I'm approaching is 1. Because these limits aren't the same, the limit at that point does not exist. Okay? How about the limit as x approaches 1 of f of x? What can we say there? What's the limit as x approaches 1? 5, 4, 3, 2, 1. Well, that limit is 2. The y values from this side are approaching 2. The y values from this side are approaching 2 because the limit as x approaches 2 from the positive side equals the limit as x approaches 2 from the negative side equals a y value of 2. Excellent. What about f of 1? What's f of 1? 5, 4, 3, 2, 1. F of 1 is 3. The y value at 1 is 3. The limit and the y value don't equal each other. Sorry, they don't. However, if I consider 4, the limit as x approaches 4 of x, what's that? Well, the y values are approaching 3. The y values are approaching 3 from both sides. And what do we know about f of 4? Well, f of 4 is the value of that point, which is 3. So sometimes the value of the limit and the value of the point are the same. In fact, most of the time. but sometimes they're not, like over here at x equal to 1. Okay, great. Now, what about this? The limit as x approaches 0 of sine 3x over 2x. Can you evaluate that one? Okay, so I'm thinking about the limit as x heads to 0 of sine 3x times the limit as x heads to 0 of 1 over 2x. I know if I do direct substitution, I get 0 over 0, and so I'm not even going to waste my time with that. I'm just going to say, okay, now this, as x heads to 0, this could be 1 if I had a 3x on the bottom. So I'm going to multiply by 3x here, which means I also have to multiply by 3x here. Now I don't know this limit. I mean, that's 1 divided by 0, which is infinity, and I don't want to go anywhere near that. But let's say I take this thing and put it over here, because these are all attached with multiplication. The limit as x heads to 0 of sine 3x over 3x times the limit as x heads to 0 of 3x over 2x. Now, here we know the limit as x heads to 0 of sine u over u is 1. But I still can't do direct substitution here. I get 0 out of 0, a 0 over 0. But I can cancel these. And now that I've canceled them, the limit as x heads to 0 of a constant is the constant. So this limit is 3/2. Okay? We want to be comfortable with evaluating limits. Next, how about this one? The limit as x heads to 0 of 3x plus sine 2x over x. Again, if I plug in my zeros, I get 0 over 0. So take a minute to figure this one out, please. Okay. Did you break this up into the limit as x equals 0 of 3x over x plus the limit as x heads to 0 of sine 2x over x? I did, and I hope you do too. Now, I need these to be the same. This needs a 2, but this also needs a 2. So what can we do here? Well, these can cancel, and so now I'm looking at the limit as x heads to 0 of 3 plus, and I'm going to take this and bring it out here, 2 times the limit as x heads to 0 of sine 2x over 2x. So what do we know? We know that the limit of a constant is that constant plus 2 times, what's this limit equal to? Well, the limit as x approaches 0 of sine u over u is 1. And so this limit is 5. Okay? Okay. So that's our little review. Now, let's move on. Okay. So, think about this function 1 over x. Okay? Do you remember 1 over x? It's one of our reference graphs. Heads up to infinity, heads down to negative infinity. So, what can we say about the limit as x heads to infinity of f of x? What can we say about this limit? As x goes further and further this way, what's happening to the y values? Well, we remember that there's a horizontal and a vertical asymptote for this f of x. And so this is all about approaching a y value of 0. This limit as x heads towards infinity is the y value that we're approaching. The y value that we're approaching is 0. That works if I come from the other direction as well. As x heads to negative infinity, These y values are approaching 0. So what I want to say is that the line y equals b is a horizontal asymptote of f of x if either the limit as x heads to negative infinity of f equals b, or the limit as x heads to infinity of f equals b. So if the limits heading to infinity are equal to some number, like 0, then y equals that number is the horizontal asymptote. By the way, this is our definition of horizontal asymptote. You have gone 2+ years of doing math, knowing about horizontal asymptotes without knowing the definition. This is the definition. It's a limit definition. I'm sorry we couldn't give it to you earlier, but we needed you to know what a limit was before we taught you the limit definition of horizontal asymptotes. Okay, so now what? Well, let's take a look at this. Where am I? Here. So let's say the limit as x approaches positive and negative infinity of 2 plus 1 over x. So what can I know here? Well, I know that this is going to be, oh, you know what? I want to use a limit property, but our limit properties have us approaching a number. And this is approaching infinity. Hold this thought a moment. Let's talk about limit properties using infinity. So it turns out that these limit properties are all the same. So we said 2 videos ago, as x approaches a of f of x plus g of x could be written as the limit as x approaches a of f of x plus the limit as x approaches a of g of x. Remember that property? Well, it turns out that the limit as x approaches plus or minus infinity of f plus g is also the limit as x approaches infinity plus or minus. The limit as x approaches plus or minus infinity of f plus the limit as x approaches infinity plus or minus of g. So all those properties that we had for limit approach as x approaches some number, they also hold true for our infinities. So I'm not going to worry about that. But I do want to point out that something does happen. Something is different. Remember this limit, the limit as x heads to 0 of sine x over x, and how that was equal to 1? And we showed that a couple of different ways. And we also found out that the limit as x heads to 0 of x over sine x was also equal to 1. And that's still good, true, and always correct. However, the limit as x heads to infinity of sine x over x and the limit as x heads to infinity of x over sine x, these are different. These are different. So what can we say about them? Well, we can say this. As I plug in an infinity here, this gets monstrously large. As I plug an infinity in here, well, sine just keeps vibrating back and forth between 1 and negative 1. So this is going to be some finite number. This is going to be a number, right? Some number between negative 1 and 1. This is going to be infinity. So what if you have a number of pizzas divided by an infinite number of people who come to dinner? 5 pizzas. even a million pizzas, but an infinite number of people come to dinner. When you have a number divided by infinity, that's going to be 0. No pizza for you. Now, in this case, I've got an infinity divided by a number, and that's going to still be undefined. Or you could say, you could actually say infinity on that one. So, some things aren't the same. And watch out, because on tests, people are so used to these that when this shows up, instead of saying 0, they say 1. So watch out for that. Okay, where am I going next? Oh yeah, I wanted to take a look at this one. So the limit as x heads to plus and minus infinity of 2 plus 1 over x. And what I thought I wanted to do here was split this up. Okay, so what do we know? The limit of a constant, 2. It doesn't matter whether x is 1 or 7 or negative 100 or positive 12,000. This is the line y equals 2. The y value is always going to be 2. Over here, what's the limit of this function as x heads to infinity? Well, we saw the graph. As x heads this way, what are my y values doing? They're approaching 0. So this limit is equal to 2. Okay. What about the limit as x heads to plus or minus infinity of 5 over x squared? Well, I can break this up with my log properties into the limit as x heads to plus and minus infinity of 5 times the limit as x heads to infinity plus and minus of 1 over x times the limit as x heads to plus and minus infinity of 1 over x. And we can evaluate each piece. We know that this is 5. We know that the limit as x heads to infinity of 1 over x is 0. And we know the limit as x heads to infinity of 1 over x is 0. So 5 times 0 times 0 is 5. No, it's 0. All right, so I know this limit is 0. In fact, I could just start over here and say, okay, I got an infinite number of people coming to dinner, squared. It's a really big number, isn't it? And 5 pizzas to feed them. You're not getting any pizza that night. All right, so we might be able to then generalize and say the limit as x heads to plus or minus infinity when you have a constant over x to some power, this is always going to be 0, okay? Because you're going to have a finite number of pizzas divided by an infinite number of people coming to dinner, so you're always going to have no pizza. This is the no pizza rule. Okay, so what about evaluating some of these other things? So the limit as x heads to infinity over x over square root of x squared plus 1. So, yeah, problems like this make students angry because I'm not about to use one of my limit properties. Here's what I'm going to do. X is heading towards infinity, and then I'm going to square that big number. Now, if I have x equals a trillion, and then I square a trillion, anyone going to notice if I add 1 to a trillion squared? Yeah, no, not really. As x heads to infinity, this plays less and less and less of a role. Now near 0, this is terribly important. In the center of the graph, this plus 1 is very important. But as x heads to infinity, this is doing squat. So I'm going to cover it up and say square root of x squared. Square root of x squared is x. And then I still can't evaluate this limit because I get infinity over infinity. And by the way, infinity over infinity is like 0 over 0. It's an indeterminate form. It's our other indeterminate form. And so we can't do direct substitution yet. But I see a number divided by itself here, and I'm willing to say but that's 1. 1, 2, 3, 1, 1, 1. And so the limit of a constant is that constant. Okay? Yeah, this whole thing about hiding that because this is growing really large, no, really, it's a thing. Now, what happens if we head in the opposite direction? Right? What happens if this is now negative infinity? Where does that take us? Let's look at that. See if you can do this one. What changes? What do you notice? Okay, so I do the same thing, and I say, okay, the limit as x heads to negative infinity over x, square root of x squared is x, and then do I get 1 again? Because the limit as x heads to negative infinity of 1, right? Because a number divided by itself, is that what I'm supposed to do here? Well, let's take a look on the graphing calculator, because I just want to see what it shows me. So I'm going to type in this function, x divided by square root of x squared plus 1 close parentheses. Okay? And I'm going to go over to the table, and I'm going to type in some negative numbers. Why am I approaching negative 1 and not positive 1? This is negative 1. How come? Well, talk about playing fast and loose. Hey, remember this? Well, we showed in our pre-cal review that that wasn't true. We know that the square root of x squared is not actually x, it's the absolute value of x. So this, with positive infinity, we'll go back to the last problem, is x over absolute x. Okay? And that is going to be, as we head towards infinity, these will all be positive. This is always positive. Positive divided by its positive self is 1. So that worked out fine with the positive direction. But now let's head in the negative direction. Now, as x heads to negative infinity, and I do x over absolute x, so this is always going to be positive because the absolute value of any number is positive except 0. And then I'm putting a negative here. So yeah, this is a number divided by itself, but this is a negative number divided by a positive number, and as a result, I get negative 1. So pay attention. That's what you need. Okay, how about this one? The limit as x heads to infinity of 5x plus sine x over x. Why don't you evaluate this limit? Come back when you're done, or if you're stuck. Okay, so just like we did with limits approaching finite values, I'm going to split this up into 2 fractions. X is infinity of sine x over x. All right, so what can we say here? What do we know? Well, we know that here we can rewrite this as the limit as x approaches infinity of 5. And here, we figured this out a few minutes ago, didn't we? This is going to be some number between negative 1 and 1. This is infinity dividing into that sum number. Sum number divided by infinity, 0. The limit of a constant is that constant, and so I get 5 here. Okay? Okay. Now, there's one other thing I want to talk about with you in this video, and that is, well, let's take a look at this situation. The limit as x approaches 0 from the positive of 1 over x. What's that? You can think about it graphically. Come on. Here's 1 over x. Whee! From the positive side, as x approaches 0, this is infinity. What about the limit as x heads to 0 from the negative side of 1 over x? Whee! That's negative infinity. Okay, what's happening here on our graph of 1 over x at x equals 0? Well, we know that at x equals 0, there's a vertical asymptote. And so guess what? The line x equals, sorry, it's a vertical asymptote, x equals a is a vertical asymptote for f of x if either the limit as x approaches a from the positive of f of x equals plus or minus infinity, or the limit as x approaches a from the negative side of f of x is equal to plus or minus infinity. Which means whenever we're approaching a point, like x equals a, whenever we're approaching a point, if the value of that limit is infinity or negative infinity, we know we have a vertical asymptote at that point. That is our definition of vertical asymptote. Now, I will say that there are a lot of students who say, oh yeah, that makes sense to me, and then by the time we get to the test at the end of the unit, they can't tell me the limit definition for vertical asymptote. So please make sure you can explain why this tells me I have a vertical asymptote. That's my definition. That's what I need to know. So please make sure you know that. Please make sure that when we see x approaching a point, the limit equal to infinity, that's a vertical asymptote, as opposed to limit as x heads to plus or minus infinity equals some number, then y equals c is a horizontal asymptote, right? We're able to define both horizontal and vertical asymptotes now in terms of limits, and so we should be mindful of that. Okay, so here's the last thing I want to look at with you today is this. Find the vertical asymptotes for f of x. Okay, so what can we say about vertical asymptotes for f of x if f of x equals 2x plus 3 over 3x squared plus 7x minus 6. So, what do you know? Well, I know that if the limit as x approaches c for f of x is infinity or negative infinity, then x equals c is a vertical asymptote. So, we know from our work in Algebra 2 and our work in pre-calc that the limit as x heads to negative 3, the limit as x heads to negative 3 of f of x equals, well, what am I approaching? Kind of have to graph it. There's negative 3, that's negative 1/2, that's negative 3/2. I have another vertical asymptote here at 2/3, and I'm doing that. And what about over here? If I plug in a negative 4, I have negative 5 on top. Negative 12 minus 2 is negative 14 times negative 1. So I've got a negative divided by a positive, which is a negative. So my graph looks like that. The limit as x approaches negative 3 from the negative side is negative infinity. And the limit as x approaches negative 3 from the positive side of the function, well, that's headed up to positive infinity. Because these limits are heading towards infinity, we say x equals negative 3 is a vertical asymptote. Okay. And over here as well, right? So we're going to say, I guess I want to put in something bigger than 2/3, like 1. That's going to be 5 on top. 3 minus 2, 1. 1 plus 3 is 4. So I've got a positive divided by positive, so I'm up here. Okay, so then I can say there is also a vertical asymptote at x equals 2/3 because the limit as x heads to 2/3 from the positive side of f of x equals infinity, and that would be sufficient, and the limit as x approaches 2/3 from the negative side of f of x equals, we're headed down to negative infinity there. And because these limits are heading to infinity or negative infinity, that means at x equals c, we have a vertical asymptote. All right, so we'll spend the next video talking about limits involving infinity. But I think that's about it for today. You know, maybe it'll be worth this conversation. Okay. Things I'm supposed to know. Infinity plus infinity. Yeah, that's it. Infinity times infinity. Yeah, that's infinity. An infinite number of pizzas divided by a finite number of people. Yeah, you get an infinite amount of pizza. Infinity times a constant. 5 times infinity is still infinity. Okay, what else can we say? We can say infinity plus a constant. If I'm going to infinity for lunch and you say, oh no, go 1 more mile, I'm not going to notice the difference. Okay, infinity minus a number, yeah. Okay. Oh, and here, because we're dividing by a, we know that a can't be 0. Okay. And in this one, that's also true. We can't have 0 because it turns out that 0 times infinity is another indeterminate form. So we're going to just put a little, yeah, you can't be equal to 0. All right, and then the last thing that I wanted to say was, you know, when we have an infinite number divided by finite, that's infinity. If I have a finite number divided by infinity, you're not getting any pizza. Okay, so big numbers divided by small number is infinity, and small number divided by big number is 0. Okay, nice. All right, I think we're all set then. Really doing the homework. Some of these are very easy, and some of them are not so easy. Okay. Oh, do we have to do that? I'm going to put that in the next video. Do I suddenly realize that this? Oh, microscope worksheet. Okay. So we do have a little more to do. Let's take care of this a little more. So, I want to approximate the slope at a point. We said before that average rate of change was the slope between 2 points, but now I want to consider the slope at a point. Okay, like we could say A, average velocity, is the slope of the position function S of B minus S of A over B minus A. Okay, that's average velocity. This is the position function. If we find the slope between 2 points, this is on A to B. Okay, but I'm also asking about instantaneous velocity. That's velocity at time equals c. And if that's the slope across an interval, this is going to be the slope at a point. Now, I have a slope formula, y2 minus y1 over x2 minus x1, and that slope formula seems to require two ordered pairs. However, I'm talking about finding the slope at a point. So in order to find the slope at a point right now, this will change soon, but right now, we've got a way of doing it. And let's take f of x. Here's f of x equals x squared. And let's take our reference points, negative 1, 1, 0, 0, and 1, 1. And let's see about finding the slope at each of these points, or at least approximating the slopes. Approximate. At each point. And the way I'm going to do that is kind of weaselly. I'm going to pick a point wicked close. I'm going to pick a point wicked close to that point. And when I say wicked close, I want 0.9999999. Now, what's the y value there? Well, I don't know. I haven't plugged it into the function yet. So I'm going to take out my calculator, and I'm going to say, what's 0.999999999 3, 1, 2, 3, 4, 5, 6, 7, 8. Good. I want to find out what this thing squared is, and I get 0.9999999 1, 2, 3, 4, 5, 6, 7, 8. Okay. Because now I have these two ordered pairs. And they're not the same point, but they're wicked close. So I'm going to type in this one minus this one. No. That's an x value. I want these y values to go on top. 1 minus 0.999999999. 3, 4, 5, 6, 7. 7. Is it really 7? 1, 2, 3, 4, 5, 6, 7. Yes. 8 over 1 minus 0.99999. Now, notice, I didn't make up this number. I made up this number. It's a wicked close number to that one. I just made it up. But this y value, I can't get it unless I take this x and plug it into that function. Okay, so don't forget the parentheses on top and on bottom when you evaluate. Parentheses 1 minus 0.1, 2, 3, 4, 5, 6, 7, 8. Divided by, close parentheses, open parentheses, 1 minus 0.1, 2, 3, 4, 5, 6, 7, 8, close parentheses. The slope is 2. Isn't that nifty? I can approximate the point, the slope here at this point is a slope of 2. Great. Now, why do I want that? Well, here's what I want you to do with this, and we'll repeat the process here. But what I'd like to do, we have a graph of f of x right now. Well, I'd like to make a graph of the slopes of f of x at various points. Now, when we want to talk about the slopes of f of x, we say f prime. So I want to make a graph of f prime. Okay? What can you tell me about this function f prime, which represents all the slopes of f of x? Well, we know one thing is that at the point 1, 1, we have a slope of 2. Okay? Now, what about at 0? So I've got one ordered pair, and let's choose another ordered pair. 1, 2, 3, 4, 5, 6, 7, 8, 1. Wicked close. Can I just make up a number here? No, I have to take this and plug it in there. Great, so let's do that. I've got 1, 2, 3, 4, 5, 6, 7, 8, 1. Square. 1, times 10 to the negative 18th. Okay, 1 times 10 to the negative 18th. Okay, so there's my second ordered pair. My first ordered pair is 0, 0. So if I do the slope formula here, I'm going to take this y value minus this y value, 0 minus 1 times 10 to the minus 18th, over this y value minus this y value. 0 minus 0.1, 2, 3, 4, 5, 6, 7, 8, 1. Okay, let's see what we get. So, times negative 1. Good, that's the top. And now I want to divide by 0 minus 0.1, 2, 3, 6, 7, 8, 1. Now, this 1 times 10 to the negative 1 times 10 to the negative 9th. So that's 0.1, 2, 3, 4, 5, 6, 7, 8, 9. 9, and with the decimal place once, twice, 3, 6, 7, 8, 9 places. So that's going to be a 1. That's the number. Okay, so what number is that? Well, I hate to tell you, but that's awfully close to 0. And if we went even further, then this would get even further closer to 0. So my slope here, my slope here should be 2. I think I've done something wrong. It's good to know where you're supposed to be going. Let's try this again. Oh, no, it's not. It's supposed to be 0. Sorry, yes, the slope here is 0. And I can see that I have a 0 slope there. Okay. And then what about the slope over here at negative 1? So again, I've got this one ordered pair, and now I'm going to try this other ordered pair. 1, 2, 3, 4, 5, 6, 7, 8, and 1. And I'll find the y value there by plugging this into x squared. So negative 1.123, 4, 5, 6, 7, 8, 1. And let's put that all in parentheses. And then squared. And so I get 1.00. 1, 2, 3, 4, 5, 6, 7, 8. 3, 4, 5, 2. Okay, so there's my second order pair. So I'm going to do 1.1, 2, 3, 4, 5, 6, 7, 8, 2 minus 1 over negative 1.00000001 minus 1 minus a negative 1 minus a negative 1. All right, which I guess is going to be plus 1. So I pull out my calculator and I do parentheses 1.123, 4, 5, 6, 7, 8, 2 minus 1 divided by okay, minus 1 divided by negative 1.23, 4, 5, 6, 7, 8, 3, 6, 8, 3, 6, 8, 1 plus 1. And I get a slope of negative 2. So here, the slope is negative 2. The slope at that point, at that ordered pair, the slope is negative 2. So what did I have to do? I had to use the slope formula, use the slope formula, use the slope formula. Now that I have all these slopes, I can make a graph of, if this is f of x, I can make a graph of f prime of x. F prime of x represents the slopes of f of x. And so what do we know? Well, we know at x equals 1, I have a slope of 2 on f prime of x. And at 0, we have a slope of 0, because that was 3, 4, 5, 6, 7, 8, 9. That's pretty much 0 there. And then we have down here at -1, we have a slope of -2. Okay? Now, when you go, so this is my graph of f prime. This represents all the different slopes on that function. I'd like to talk about what function this is the next time we're in a synchronous Zoom together. But see where on assignment 28 it says microscope worksheet? So you go over to Office 365 and you check in the Chapter 2 assignments folder and you'll see a microscope worksheet. And the microscope worksheet has 4 f of x's on it. This is one of them. So we've just done 25% of that assignment, except you need to write down all the slope formulas on the page. So write down all the slope formulas on the page. If you just tell me what these slope numbers are without actually showing me the work finding the slope, then I don't give you any credit. You have to show me. Think about it as the credit for this worksheet is because you had to do the slope formula once, twice, 3 times on this function, and then you had to do it some more times, right? Because there's a total of 4 functions. You're going to do the slope formula 3 times with each of them. So you're going to have to do this nasty slope thing 12 times. And hopefully, after this assignment, we'll have a way to do it that doesn't require us to use a wicked close point to approximate the slope at a point. Okay? Fabulous. I think we're set and ready to go. So have a wonderful day, everyone.